All right, so before we start talking about the quantum theory and the electronic structure of atoms, first thing we need to do is to back up a little bit and talk a little bit about energy and energy changes, because we will be using some of this information as we explain quantum theory and electrons and atoms. So, when we defined chemistry early on, we said that chemistry is the study of matter, the changes that matter undergoes, as well as the energy associated with those changes. So let's first of all take a look at what energy is. And we can define energy as simply the capacity or the ability to do work or transfer heat. So if you just think of it on a general sense, if you have a lot of energy, right, you can do a lot of work. And in the case of chemical reactions, we're also looking at that in the transfer of heat. So all the forms of energy, and energy comes in a variety of forms. We can have two main categories. We have what's known as kinetic energy or potential energy. And the difference between them is fairly straightforward. So kinetic energy, which we often abbreviate as KE, or more technically as E, so uppercase E subscript K, so E sub K, sub there meaning subscript, is the energy of motion. So anything that is moving, any type of motion, right? Whether it is a person walking, whether it's the wind blowing, whether it's a person swimming, whether it's gas particles zipping around a room, right? If they're moving, they possess kinetic energy. And kinetic energy is defined mathematically as 1/2 of the mass times the velocity of that particle squared. Okay, so in our equation here, let's just represent it or write it a little differently so it may seem a little bit easier to understand. So we have a half m times u squared. So m here is the mass. And then u, this symbol u that your book uses, is velocity. Okay, sometimes other books use v for velocity. Okay, you can think of velocity as the speed of something in a particular direction. Okay, and if you get into physics, you'll talk about vectors and all that stuff. That's what it is. So velocity is the speed of something going in a particular direction. So a half mv squared or a half mu squared would be the formula for kinetic energy. So there are all different types of examples of kinetic energy. One that we're going to focus a lot on in our class is something known as thermal energy. And thermal energy, we often refer to that as heat, but it really is thermal energy. I'm going to put heat in quotations. But it's a form of energy that's associated with the motion. Again, atoms and molecules moving around possess some sort of thermal energy. And that's going to be important when we start looking at the definition of temperature a little bit later on. So that's kinetic energy. We define as half mv squared, the energy of motion. Potential energy, which we can abbreviate as PE, or sometimes you'll see E with a P subscript, is the energy possessed by an object due to its position, so where it is, or its composition, what it's made up of. Okay, so you think of potential energy sort of in a macro sense. If you think about the water in a dam, okay, the water that's behind the wall of the dam has a lot of potential energy. It has the potential to generate energy to do work. If you think about, a boulder at the top of a hill. Okay, so there's a hill over here, right? There's a boulder. Let's say it's perched on the edge. Okay, it has the potential to do work as it goes down the hill. Now, when we start looking not macroscopically, but microscopically and even submicroscopically, we're going to find two forms of potential energy that are going to be really important for us. And that's known as chemical energy, which is the energy that's stored within the structural units of chemical substances. So for example, energy that's stored in compounds and molecules. Okay, so for instance, the energy within, I don't know, something like gasoline. Or something in other types of fuels, right? The energy that you find in stuff like foods. Okay, the fuel that we use, glucose, for example, which is a sugar. But pretty much any food that you eat contains energy in the form of chemical potential energy. Another type of energy, potential energy that we're going to see is electrostatic energy. And that is the potential energy that results from the interaction of charged particles. So charged particles, something that has a charge on it, can be either positive or negative, right? Those are your charged particles. And electrostatic energy, so E subscript EL, is proportional to the charges that are involved divided by the distance between them. So we can say E sub EL is proportional to, so this symbol here is a proportional sign. It kind of looks like the alpha symbol we saw earlier on. So here it means proportional to the product of, so Q1 and Q2 would be your charges of your particles. And then D would be the distance between them. Between the charged particles. So the way that proportionalities work is we can actually take this proportionality, we can turn it into an equation, but let's talk a little bit about what this actually means. So if we say the electrostatic energy, potential energy is proportional to the charges, the magnitude of the product of the magnitude of the charges, what this means then is the greater the charge, the greater the electrostatic potential energy, right? So we can say the greater the charge, the greater the EL, right? So as this term in the numerator increases, then the energy increases as well. So what this also means that is in the case of the denominator D, the distance between them, as D decreases, so the smaller the distance, so if the denominator becomes small, then this entire thing becomes big, right? So that means the energy would be greater. So that's known as an inverse relationship. And we'll see those types of relationships down the road when we look at gases especially. So we can take this relationship, this proportionality relationship, we can turn it into an equation. We can say the electrostatic potential energy is equal to, so we're introducing this equality sign now. And when you take that proportionality and you make it into an equality, you have to introduce a proportionality constant, which we're going to refer to as C. Okay, that's your proportionality constant. And everything else is going to remain the same, right? Constant means it doesn't change. So C times Q1 times Q2 over D. Okay, so either way, if that number doesn't change, the relationship still holds true that we talked about previously in terms of E being proportional to the charges and inversely proportional to the distance between those charges. We'll take a look at some calculations here in a second. So one thing to keep in mind as we start looking at energy changes is that energy can be interconverted from one form to another. And that is really, really critical because it stems from a very important law in science and a law in chemistry and a law in physics called the law of conservation of energy. So in a nutshell, what that means is energy is conserved in the universe. So energy in the universe is conserved. So that means, by extension, that energy can neither be created nor destroyed, but it can be converted from one form to another. Okay, all different types of energy. Some forms are more useful than others. Okay, and a lot of time, thermal energy or heat is, one form of energy that is other forms of energy are converted to, and because it's not really useful in some cases, we think of it as being lost, but it's not actually lost. It's just being converted to a less useful form of energy than other forms of energy. So the interconversion of energy is critical for science, and it's critical when we study chemistry, when we study all the different sciences, and that's part of the law of conservation of energy. So when we start looking at energy, we measure energy in various units. The SI unit of energy is called a joule. So Joule, abbreviated uppercase J, and that's named after scientist James Joule. And it's possessed, that amount of energy is possessed by moving a 2 kilogram mass at a speed of 1 meter per second. So if we plug these values into our kinetic energy equation, right, and again, this doesn't look as user-friendly as the way that I'm going to write it. The kinetic energy of that mass would be 1/2 the mass, which is 2 kilograms, times the velocity squared. So the velocity there is, or the speed, 1 meter per second. So 1 meter per second, and then this entire thing would be squared. So if we look at our units now, we have 1/2, we have 2 kilograms, right? Meter times meter would be meter squared. Second times second would be second squared in the denominator. Okay, so all this comes after it. And if we now evaluate this, obviously the twos are going to cancel. So we end up with kilogram meter squared per second squared. Okay, and 1 is understood. That's what the joule is. So a joule then is the same unit as kilogram meter squared per second squared. So we can relate that energy to other units, mass units, and then a distance unit, time unit as well. We can do all sorts of conversions if we wanted to. We can also define a joule as the amount of energy exerted when a force of 1 Newton, abbreviated uppercase N, is applied over a distance of 1 meter. So 1 joule is the same as 1 Newton meter, which is the same as 1 kilogram meter squared per second squared. Okay, so all of these are referred to the same amount of energy. Because the joule is so small, we often use a larger unit. So for example, we use a kilojoule, symbol small k, big J. And again, kilo of anything means 1,000 of that thing. This is a metric conversion. You should know this. Okay, you should know all your metric prefixes we talked about in weeks 1 and 2. So kilojoule, 1,000 joules, megajoules, a million joules, etc. All right, so if we take a look now, calculating the kinetic energy of a helium atom moving at a speed of 125 meters per second. All right, so provided with a question, fairly straightforward question. We need to organize the information like we would in any question. So if you want to calculate the kinetic energy, so E sub K would be equal to 1/2 mv squared. Okay, we know we're given in the problem what V is, so that's V over here. So we can plug that into our equation, right? So we have this term. What we need is M. We need the mass of a helium atom. So we can look that up in the periodic table. And we see that the average atomic mass of a helium atom, right? That's straight from the table. We just read it as 4.003 atomic mass units. Okay. Now, if we want to plug this mass into our equation, we want to make sure that we have the correct unit. So we want to go to a metric unit of mass, and we can use the relationship between grams and AMU to convert this from AMU into grams. And then once we get to grams, then we can convert it to the unit of mass that we have in the unit of energy, which has kilograms in it, right? So that's why we want to convert the AMU to grams in the first place, so we can then convert it to kilograms. So that's outlined over here. Let's actually set this up in a way that's a little bit more user-friendly. So we have our 4.003 atomic mass units. Okay, that's the mass of the helium atom. I'm using the AMU to grams conversion. So according to, we can look that up in your textbook. One AMU is 1.661 times 10 to the negative 24 grams. Remember now, the AMU is a very, very, very small unit. AMU goes away, and then we have our grams to kilograms. So 1 kg is the same as 10 to the 3 grams, right? Or 1,000 grams. Whoops, I have my unit in the wrong place. My apologies. The unit should tell you where to put them. So 1 kilogram actually goes on top, because we want kilogram as our unit. So that has to go on the numerator, and then that's 1,000 or 10 to the 3 grams. So grams go away, and we end up with kilograms as our unit. We evaluate that, we end up with a very, very, very small mass. So this is M. Okay, and then our velocity, so we plug that into our equation. Our velocity 125 meters per second, then that's squared. So don't forget now, it's a half mv squared. So we have to square that velocity and then times it by the mass, divide everything by 2, and we end up with 5.19 times 10 to the negative 23 joules as our unit, or as the amount of energy possessed by one helium atom moving at a particular speed. If we take a look at the other calculation determining the amount of electrostatic potential energy, I'm sorry, let's read through the question. How much greater is the attraction between charges of +2 and -2 than attraction between charges of +1 and -1 if the opposite charges are separated by the same distance? Okay, so now we're comparing. In this question, we're going to be comparing the electrostatic potential energies between two situations. Okay, so in situation 1, we have our EL being equal to our constant C times, let's say this is situation 1 here, and then this is situation 2. In situation 1, our charge Q1 would be +2. Our charge Q2 would be -2, and then that's divided by our distance D. In situation 2, our electrostatic potential energy is the same constant C times the charge now in situation 2, which is +1 times -1. Those are our charges, Q1, Q2. The distance between them is the same as above. So D is the same in both of these. So all we need to do then is just to take the potential energies and we just divide them. Okay, so 1 divided by 2 will give me that ratio, or how much more 1 is than 2. Okay, so if I substitute, or if I do a little bit of math involved here, okay, I can see then that my C is going to cancel away. I can see my D is going to cancel away. Right, and what I end up with, to simplify this, is now I have +2 times -2 is -4. I have +1 times -1, that's -1. Negative signs go away. 4 over 1 is the same as 4. So this means 1 compared to 2 is 4 times. So we say then in situation 1, where we have the charge of +2, -2, 4 times the energy. 4 times as large. So situation 1 is 4 times as large as situation 2. Okay, so here we're not actually plugging in values and calculating the amount of electrostatic potential energy. We're just comparing amounts. And in this case, we can simplify our equations by canceling out like terms when we divide them.